How invisible, microscopic vibrations of molecules dictate the survival of a massive, churning ocean ecosystem? The answer lies in the mechanics of heat. To understand these mechanics, we have to start at the molecular level. Thermal energy is the total kinetic energy of all the randomly moving molecules within a given system. If you add up the movement of every single atom, you get the thermal energy. Temperature is a different measurement. It measures the average kinetic energy of those molecules. It tells us exactly how hot or cold a body is, regardless of its total size. A small cup can have a few highly energetic molecules and a high temperature, while a giant tank might have slow molecules and a low temperature, but vastly more total energy. When these two systems interact, energy flows directly from the higher temperature to the lower temperature. That active transfer of energy across a temperature gradient is the strict definition of heat. Heat is not a static property that an object holds inside itself. It is entirely a process in motion. In the physical world, this transfer occurs in three specific ways: conduction through direct contact, convection through fluid movement, and radiation through electromagnetic waves. This flow of heat will continually operate until both interacting bodies attain the exact same temperature, reaching thermal equilibrium. Because the universe is driven by this constant transfer of energy trying to balance itself, the exact way specific materials resist this temperature change dictates how our physical world operates. To measure exactly how much heat is required to change a substance's temperature, we use a specific mathematical model. This is the heat equation. It shows that the heat gained or lost, Q, depends on the mass, the change in temperature, and a crucial variable labeled S. That S stands for specific heat capacity. It represents a substance's unique thermal resistance, the exact amount of energy in joules required to raise 1 kilogram of that specific material by 1 degree Celsius. This table provides the specific heat capacity for common substances. Metals offer little thermal resistance. Gold requires only 130 joules, and iron just 460. But further down, water has a massive capacity of 4,200 joules per kilogram degree Celsius. This value means that to raise the temperature of a kilogram of water, you must provide nearly 10 times the energy required for the same mass of iron. This mathematical property makes water a universal thermal buffer, a feature that both human engineers and natural ecosystems exploit to regulate extreme thermal environments. We apply this incredible buffering property directly to engine mechanics. Water is the ideal machine coolant because it can absorb vast amounts of destructive heat from a working engine without boiling away. This same capacity to absorb heat means it also retains heat far longer than other materials, making it highly effective for domestic uses like slow-release pain relief in a hot water bag. Scaling up from human engineering to planetary mechanics, we see this exact same dynamic at work along coastal boundaries. During the day, the land, which has a low specific heat, heats up quickly. The warm air above it rises, drawing in cool air from the sea, creating a daytime sea breeze. At night, the process inverts. The sea, with its massive specific heat capacity, retains its warmth long after the land has rapidly cooled, reversing the airflow into a land breeze. The microscopic resistance of water molecules directly flattens the temperature variations of these coastal environments, shielding cities like Mumbai from extreme seasonal temperature swings. What happens to this thermal buffer when temperatures plunge toward freezing? For almost all normal matter, the thermodynamic rule is simple. As temperature falls, kinetic energy drops and volume steadily decreases. This graph tracks water's volume as it cools. Initially, it follows normal rules, its volume steadily decreasing down to exactly 4 degrees Celsius. But below 4 degrees, the behavior inverts. Volume actually increases as temperature approaches zero. Looking at this corresponding density graph, this volume anomaly translates directly to a peak in density. Water is at its absolute heaviest at exactly 4 degrees. In a real-world environment during winter, the 4-degree water becomes the densest layer and sinks to the absolute bottom of the lake, while the colder 0-degree water becomes lighter, floats to the top, and turns to ice. This creates a layer of less dense surface ice acting as a floating shield, isolating the liquid water below from the freezing atmospheric air above. Without this 4-degree inversion, bodies of water would freeze solid from the bottom up, removing the liquid habitat necessary for aquatic survival. We can calculate the exact final outcome when materials with completely different temperatures and specific heats are forced to interact. This is governed by the principle of calorimetry, which states that the heat lost by a hot body is always exactly equal to the heat gained by a cold body. Setting the two heat equations equal to each other gives us a balanced mathematical model of this transfer. Consider a 10-gram iron nail at an extreme 180 degrees Celsius dropped into 50 grams of water at just 100 degrees. Even though the nail is scorchingly hot, the water holds vastly more total heat energy than the iron. The nail has a higher average kinetic energy, a higher temperature, but the water's larger mass and extreme specific heat capacity give it a vastly higher total kinetic energy. As they interact and reach equilibrium, the water's thermal buffer prevents its temperature from changing significantly, while the nail's temperature plummets rapidly to meet it. The variables in these equations, specifically water's 4,200 joule capacity and its density inversion, are the physical mechanics that enable both mechanical cooling and biological winter survival.